Construction of AC motors. 1. Stator. Core made of laminated steel sheets to reduce eddy current losses, forming hollow cylinder. Windings. Coils or insulated wire placed in the slots of the stator core connected to the AC power supply. An arrangement of these windings determines that the number of poles and the type of motors. 2. Rotor. Core, a laminated cylindrical structure mounted on a shaft similar to the stator core to minimize eddy current losses. Type of rotor. Squirrel cage rotor consists of conductive bars, usually made of aluminum or copper, short-circuited by end rings and both ends. This type is commonly used in induction motors. Wound rotor has windings similar to the stator windings connected to slip rings of the shaft. This type is used in wound rotor or slip ring induction motors. Number 3. Shaft. A metal rod on which the rotor is mounted. It extends out of the motor to connect to the mechanical load. 4. Bearings. Support the rotor and allow to rotate smoothly. Bearings are placed at the ends of the motor's housing to reduce friction between the rotating shaft and the stationary parts. 5. End covers, also known as end belts or end shields. These cover the ends of the motor, house the bearings, and provide structural support and protection for internal components. 6. Cooling system. Ensures the motor operates within safe temperature limits. This can include fans mounted on the rotor shaft, cooling fins of the motor housing, or more advanced cooling methods in large motors. 7. Housing. The outer casing that encloses and protects the internal components of the motor. It also helps in heat dissipation. Types and operation of AC motors. AC motors are broadly categorized into two types based on their operating principles. 1. Induction motors, synchronous motors. A. Squirrel cage induction motor. B. Wound rotor induction motor. 2. Synchronous motors. A. Permanent magnet synchronous motor. B. Electrically excited synchronous motor. Squirrel cage induction motor. Case and operation of AC motors. Operation. Magnetic field generation. When AC voltage is applied to the stator windings and produce a rotating magnetic field. Induce current in rotor. The rotating magnetic field induces current in the rotor bars due to electromagnetic induction. Torque production. The interaction between the magnetic field and the induced current generates torque, causing the rotor to rotate. Asynchronous operation. The rotor never reaches the speed of the rotating magnetic field. Synchronous speed due to slip, which is necessary for torque production. Applications. Squirrel cage induction motor, widely used in industrial applications such as pumps, fans, compressor, and conveyors due to its robustness and low maintenance. Wound rotor induction motor. Operation. Used. Starting external resistors are connected to the rotor circuit to limit starting current and increase starting torque. Speed control. By varying the external resistance in the rotor circuit, the motor speed can be adjusted. Torque production. Similar to the squirrel cage rotor motor, torque is produced by interaction of rotating magnetic field and the induced rotor currents. Applications. Manned rotor induction motor, used in application requiring high starting torque and variable speed such as cranes, elevators, and hoists. Advantages. 1. High starting torque. Provides high starting torque, making it suitable for heavy load applications. 2. Speed control allows for speed variation by adjusting the external resistance in the rotor circuit. 3. Smooth start. External resistors can be used to control inrush current, resulting in a smoother start. Disadvantages: 1. Complexity. More complex construction due to slip rings and external resistors. 2. Maintenance. Higher maintenance requirements due to additional components like brushes and slip rings. 3. Cost. More expensive to manufacture and maintain compared to a squirrel cage motor. Permanent magnet synchronous motor. Operation: magnetic field interaction. The stator windings create a rotating magnetic field when connected to an add supply. Synchronous rotation: the rotor locks onto the rotating magnetic field and rotates at the same speed, synchronous speed. No slip. Unlike induction motors, there is no slip, meaning the rotor speed is always synchronized with the stator field. Applications: permanent magnet synchronous motor used in application requiring high efficiency and precision such as robotics, electric vehicle, and HVAC systems. Advantages: 1. High efficiency. Very efficient in converting electrical energy to mechanical energy. 2. Precise speed control. Maintains a constant speed irrespective of load variation. 3. Compact size. Smaller and lighter compared to induction motor of the same power rating. 4. High power density. Suitable for high performance applications. Disadvantages: 1. Cost more expensive due to the use of permanent magnets. 2. Complex control. Requires sophisticated control systems such as inverter or drives. 3. Demagnetization risk. Permanent magnets can lose their magnetism and exposed to high temperature or adverse condition.